right now. Okay.
Well, I don't.
Steal the iPad. It's like 2 meters face. I'll take the iPad.
Okay, because apparently that's getting you distracted. All right. So I want to go over your lever setup because that's probably the thing that is most difficult to remember. And so you have, there are 3 different labs. There's 2 different lever labs and one of the topics that are on that sheet of paper. I have the sheet of paper, I don't know by heart. Okay, so I will go over each of the topics, but I'll first start with the demo of the different levers. So first class lever, what do we have? Yeah.
Fulcrum in the middle.
Fulcrum in the middle. So let's get my fulcrum in the middle. Okay.
It's rolling.
It's recording. Okay, so I put it at 50. Next.
Oh, you have to put. Oh, depends on what the lot says. You have to.
Okay, so in the lab that you guys did, you had to determine whether there was, whether increasing the lever arm length provided, like what happened to the effort when you increased or decreased the lever arm length versus load arm. That, you're going to have maybe something similar, so you have to make sure you know the difference between lever arm and load arm. Okay, so for now, place them anywhere. So if we're looking at the effect of the lever arm, then we're going to place the load and not move the load. Okay, so you place it at one end. I'll place it at 10, just because it's nice and easy that way. Okay, and place this at the other end. So I'll place it also, I'll place it at the 90, and then we see what? We see that they should be equal, right? So I would place this. For this, make sure you're checking that it works properly. So right now, this one isn't calibrated very well. So you can use the screw up here to calibrate it. So that just like tightens the spring or moves the spring up. Always, if you're checking the calibration, just pull on it and let it go, and that'll be where it is, okay? The weight. I want to be hanging over the edge. Makes it easier. Okay, so wherever you're calibrated to, so right now it's calibrated so that the bottom is at 0. So when I read it, I'm going to read the bottom. So, and you pull down, and you're pulling down until parallel, right? Your meter stick should be parallel to the table. Okay, and you'll take your reading. Okay. That's first arm, and then if I'm checking the effect of the lever arm length on it, like we did in lap, you can change it. So you can bring it closer, you can bring it further. Like if I started close, then I'd bring it further. Here, this might actually be positioned differently. So you'll just go based on whatever instructions. Now, what do I need to change here to make this a second class lever?
The load in the middle and the fulcrum.
Okay, so I can pick the end for the fulcrum. All right, and load in the middle. Okay, and since it's down, this I lift up. Okay, again, you're lifting up until parallel. Okay, and you got to make sure, like for a second there, my dynamometer did stick, so I'm gonna take a second reading to make sure, since it did stick when I did it. Okay, when I lifted, it didn't. It didn't like. Yeah, it wasn't. Like you could check it by doing that, because before when I went up, it wasn't working properly. Okay, so this is not a very good one. Okay, and that's my second class lever. All right, when you're done, you dismantle it all. I would wait until you're done, like, finish your write-up in that, because you don't want to be taking away from the time it takes you to write and do any calculations and make your conclusions. Here I have time, so I will. We're not the only class using this stuff. All right, so that is, why don't I use this one for, like, this same setup for my third class lever?
Because the effort's in the middle?
Because, well, when we put our effort in the middle, I basically end up just lifting the whole thing off of this support. So I need to really make sure my fulcrum is anchored.
That's why you use like the long.
Yeah, and there's also, why do I have 100 gram mass and not the 500? Like, why am I not going to use the 500?
Because
Well, it's too heavy, but why? What's going to happen?
Oh,
Yeah, so what does that mean for my MA?
it's gonna be below 0.
And it won't be a
I
third.
mean less than 1.
It's going to be less than 1, right? So my effort is going to be much higher. So if I'm using 500 and I only have a 5 Newton, if I only have a 5 Newton dynamometer, I won't be able to read it, take a reading, okay? So we have different dynamometers. We have 10, 5, 2.5. It's all the same. They're just different scale. So this is the third class lever. Okay, so you have to place it on the retort stand. Make sure you know all the proper words, right? So this is the lever, this is our fulcrum, these are our masses, or we could just call these clips, not particular, and your dynamometer. Okay,
Do we need to call those master, or can you just call them load?
you can call them load. Yeah, you can call them. The reason we're not using weight is because what is weight? What units is, no, it's not mass. Weight is not mass. Weight is in newtons, right? We measure weight in newtons. So weight or force is equal to mass times gravity.
times force times gravity.
Mm-hmm. Okay, yeah.
Will we have the formula?
You will have the formulas. Okay, so my load, so fulcrum. Put our mass on, and then we just lift, again, parallel, as best you can, right? Either way, your results will show.
Wait, Miss, doesn't the effort have to be the middle?
Mhm.
The effort, does that have to be the middle?
There you go, good. Well, how many people actually noticed that? Okay, well, only a couple people said it, so that I was doing a second class lever and not a third. Okay. What?
Were you testing us?
Yes. I was, though. Okay, so.
Put it in the middle.
Yeah. Oh yeah, the dynamometer. There's a dynamometer.
I'm just waiting for them to settle down over there. Gentlemen, can you stop, please?
What is going on?
Okay, so what should you notice here?
The dynamometer is in the wrong spot.
No, it is not. I'm just going to get what?
Not mechanical reaction.
It should be equal to about 1, right? If everything is, because my lever arm and load arm distance, so even if we went by distances and not forces, then they should be about the same. Just like one of the first things you should do before you even attach the mass, like your mass to your lever, is you should be checking what the weight of it is. So here I'm getting a weight of 1. It's pretty right on. And then here I'm getting a weight of 1.3. Okay, so it's slightly off. Either way.
It should be 1 exactly.
Yeah. So I'll keep my load there, and then I can move along, and I should see an increase or decrease.
Increase.
Okay.
No, increase.
Then the amount of force should be increasing.
Mechanical advantage.
Yeah, mechanical advantage
In the lab, we're
decreasing.
supposed to get all 3.
And so for the lab exam, it's one of the 3 types of levers.
No, I'm saying, are you supposed to test all 3 anchors?
I don't understand what you did. Like, you did, like...
In which lab? The lab you guys did or lab exam?
Oh, lab exam.
Okay, so lab exam, you could be given one of the 3 levers. You could have to do lever 1, lever 2, or lever 3.
But say we're doing lever 3, what you did there. Which hook are we supposed to put the dynamometer on?
Review your lab.
Okay.
Okay? Now, the thing is, so we have lever 1, lever 2, lever 3, but we also have load and lever variations. So there are 6 different lever labs. Okay? So talking to your friend in the other class, not gonna help you, because the combinations don't match up. Like we have between the 3 labs here plus the lever lab, there are 9 different labs. So 9 different labs for the few different classes, so no class has the same combination. So good luck with, if you are talking to someone in the other class. So, next thing. Okay, so those are your lever demonstrations. All right, so here it says Intro to Microscope. I'm recording it right now. I'll export it as a video. So, introduction to microscope. Now, it's not because you're going to have a lab on the microscope. It's because you need to know how to operate a microscope. So, know how to prepare a slide. Okay? And know how to operate a microscope. Okay, so here it says preparing mixtures, homogeneous mixtures, and soluble, insoluble salts. So either way, we're looking at mixtures, pure substances, okay, under the microscope. So you would not be... All right, so how to prepare a microscope slide for a liquid. Anyone remember how to do that? Carmine?
You take one of those like little square pieces of the glass.
Yeah.
You take the distilled water thingy and you put a little drop of water on it.
Well, that would be if we were doing it just for the water. So if it's for any other solution, you can use a dropper to put some of that solution on the slide.
Okay.
And then what was the last thing we did? You need a cover slip. Yep. Okay, so you'll put a drop of mixture, solution, whatever it is, okay? Because you don't know what it is.
So you'll just give us like, okay.
Yeah.
So, and the last one we did, it was water, but we won't know what it is.
Well, no, we did with tomato juice, we did with milk, apple juice, right? Vinegar. There were a few different ones. Okay, so put a drop of mixture solution on a slide.
We did the newspaper like we used the water.
Exactly. When it was the news, but we're doing mixtures, right? So put a drop of mixture solution on a slide. Put a cover slip on top. Okay, so that'll protect it from slipping around, like you're not going to lose your drop as you transfer it to the microscope. Also, it'll prevent anything from getting onto your microscope lenses. Okay, next, operating a microscope. How do we start? Okay, well, I mean, that I hope is a given. I mean, it's not wrong. Okay, you course focus first, but what do I need to make sure?
Check your magnification.
Check your magnification. Where does it have to be? Lowest. Okay, does anyone remember what it is?
4.
It's 4.
Oh, 10, 4.
The eyepiece is 10. The eyepiece is 10. We don't have to worry about that. 4 is the, your 4x is the lowest. Okay? and you will adjust the coarse focus. Okay, so you're adjusting the coarse focus until your solution is in view. So until your mixture is in view. Okay, and then you adjust the fine focus until you see clearly. Okay, once you see it clearly. All right, now watch out for some of the things. If your solution, like if your mixture, it looks clear, like if it's colorless and transparent, and it goes under the microscope and you start seeing particles, chances are those particles are just dust, right? But if it's a cloudy mixture and like it looks like a single substance, and then you put it underneath and all of a sudden it's nice and clear, then like you can see the different particles and stuff, then chances are it's a colloid. Okay, if you can't see anything under the microscope and the solution has a color, then it's a solution, right? So a homogeneous mixture. So just watch out. If it's colorless, chances are like anything you see under the microscope is dust. So just watch out for stuff like that. Okay. Any questions about operating a microscope?
To get the total magnification, do you do like the 4 times?
You multiply.
The lens times the magnification.
Yeah. But the main thing that you need for this is the operating of the microscope. Okay, so that was lab 1. Okay, all your labs are numbered, so you can go looking for lab 1, 2, 3, 4. Okay, and then the lever lab, which I just handed back last week or so. Mixtures. Okay, make sure you're comfortable with all the different procedures, okay? So preparing mixtures, I'm gonna focus, how would we prepare a mixture? Just, well, you mix things, but I mean, it depends on the type of mixture. It can be proportional or not, so it really just depends.
For a simple heterogeneous, you need like that stirring rod.
Yeah, so so either we could be measuring, so you have to be comfortable with measuring.
Wait, are we?
I'll just say measuring liquids with a graduated cylinder.
So this we're not separating any mixtures like the.
No, didn't give that this year. Okay, so measuring liquids with a graduated cylinder. You need to be able to measure the mass of a solid with an electronic balance. Okay, you need to be able to, you're using, use a stirring rod to stir the mixture. Okay, and you do need to be familiar with the different types of mixtures. Okay, so we will go over that in just a moment. All right, types of mixtures. All right, so types of mixtures, you have homogeneous and heterogeneous.
Pure substance.
But that's not a mixture. Okay, so homogeneous mixtures. What is another name for a homogeneous mixture? Amir. Solution. So what does that mean to be a solution?
The particles are separated equally.
You'll have, okay, so you have an even separation of particles.
Miss, can I say no suspended particles, or does that not work?
Well, that's starting to, I mean, that would be true, but then we're starting to talk about the definition of our potable water.
Okay.
Okay, so you have an even separation of particles. Now, what is the solution made up of?
Two different.
It can be
Soluble and a solvent?
a solute and a solute. Yeah, a solute plus solvent. What's the difference between your solute and solvent? So this one is dissolved. Yeah, we'll call it the dissolver. Okay, so the solvent dissolves, and it's the one present in greater quantity, in greater amount. Okay. Heterogeneous mixtures. We have 3 types. You gave me the first one before.
I give you a simple letter.
A simple, and what's a characteristic of a simple heterogeneous mixture? Jamal?
When phases are equally identified.
Phases are clearly identifiable.
That's like one more. No.
Yeah? Okay, so both, like I say both phases, or I mean, 3, 4 phases, doesn't really matter. You can clearly see them. So your example, oil plus water.
And they separate is it minutes to hours? No.
Separate quickly.
Seconds to
Separate quickly.
We can just say separate quickly. Okay. Number 2. Ryan? We do have a colloid. Okay, so our colloid, it looks like a pure substance. But not necessarily transparent. Okay, so it looks like a pure substance, but it's not necessarily transparent. And it does take a really, so must look under a microscope to see suspended particles.
And they take a really long time to
Yeah.
separate.
A long time to separate. Possibly indefinite.
Indefinite means it'll never separate.
Yeah, pretty much. It's like an undefined amount of time, right? Kind of like we say infinite, indefinite. Like something definite is. Okay. Number 3. You have your what?
So if you write the example for college.
Oh yeah. Okay. All right, so suspension contains suspended particles. So it's usually a liquid with it'll be on my website under lab exam, and the video will be linked to my YouTube account. All right. So it contains suspended particles. The particles separate after a defined period of time, which means they eventually separate. Well, that's not necessarily true because, I mean, in mud, you can see the particles in mud pretty, or sand, you can see sand pretty quickly. Pulp, you can see with your orange juice with pulp. So that's not necessarily true. So we've got mud, orange juice with pulp. Okay, and tomato juice was one that we also saw.
Yeah, we tried
Okay. Solubility. So soluble and insoluble salts. Okay, so that was lab number 4. Okay, what does soluble mean?
It can be dissolved by the universal solvent, which is water.
Well, it doesn't, we won't go just by universal solvent, water. We could say, like, it could be dissolved in any substance, really. And you have different types of solubility. You have stuff that's, like, water soluble versus not water soluble, but you can dissolve it in something else, right? So, like, nail polish can't be dissolved in water. But as soon as you put a solvent like acetone, there it goes, right? So something that's not soluble in water could be soluble in something else, and vice versa. Okay, so soluble just means it can be dissolved, okay? And we generally would look at completely soluble, so it can be dissolved completely to make a solution. That is the definition we will look at. Okay, so we're making a solution. So your homogeneous mixture. All right, insoluble. Okay, does not dissolve completely. Does not dissolve completely or does not dissolve at all.
In anything?
Well, we're going to be focusing on water, so you weren't wrong saying water. Okay, so it does not dissolve completely or at all. Okay, so we can have different ones. Now, we actually had factors that affect solubility. So affecting the solubility of a substance or the speed of solubility, right? So, or the speed of that dissolution. Okay, because there's only one factor that actually affects how much of a solute can dissolve. Which factor is that? Temperature. So the only one that actually affects how much of a solute is soluble is temperature. So we saw generally what happens as we increase temperature. Yeah. Well, you can give the whole reasoning, right? So you can say as temperature increases, particle motion increases, therefore increasing the number of collisions between particles, so more solute dissolves. Okay? What types of solutes do not dissolve as temperature increases?
Sand?
Well, sand remains pretty insoluble, but more if you looked at soluble substances, so that would fall under insoluble. But soluble substances, those gases, remember most gases decrease in solubility as temperature increases. We won't be working with gases, but you know, just throwing that out there. Okay, so temperature. Okay, so as temperature increases, the particle motion speeds up. This results in more collisions between the particles. Therefore, increasing solubility. Okay, so that's the only one that actually increased solubility. Now there are two more that increase the rate of solubility. Surface area. Oh, stir faster, but I thought you were just saying surface weird. Stir, like, never mind. Surface area. So you increase. So increasing surface area, basically it allows more contact between the solvent and solute.
I'll be like, increasing the surface area will be like spraying more water. Sharp that.
Okay, last one is stir faster. So stir. You're stirring, which basically just increases the kinetic energy of the system as much as the temperature did. I can see you, you know. Not, I might be looking down at here, but my peripheral vision is quite good. So increases energy in the system, which increases the particle collisions. Shh, guys, just ignore it. So, which increases the particle collisions. Therefore, faster